I want to give some introduction. You're not for the purpose of representation, I'm fixing this talk to be nearby, and for most of talk you can introduce to be dealt with. And what is the categorical local Langlands conjecture? Categorical guarantee. So it predicts that there is a free space for invading for the category of representations of the group here, the lambda coefficient to the category of participant Q on the stack of L parameters. And they are quotient by the G-fast conjugate action. And also this space is defined over lambda. I'll explain this definition later. And in this talk, I will try to verify this for the zero supercuspidal path. I will define this step zero representation later. So my setting is that fix representation type of the zero bar. So it's the zero bar module with the action of GF. Irreducible. That's irreducible. That's already been over irreducible. And let's phi to be the L parameter associated to pi. So it's here is the element in way of comparison with FL bar coefficients on the function L parameter. And with trivial on the y index and this invisible. The goal is to specify this conjecture to this part. So on the representation side, I consider the block of this representation category containing pi. The representation category will decompose into some indecomposable sub-abelian category, which is called blocks. So this is a block containing pi. And on the L parameter side, I will consider the connected component containing this L parameter block. This phi is the connected component. That of L parameter containing pi. I'll compute these two categories explicitly. So this rep category, in the end, it will be identified with the category of participant sheaves on CM times the group scheme of LK to solidity. Similarly, on this side will also occur the same thing. But There's also a liberated. At least abstractly, it will be embedded here. It just embedded to the degree 0. Time permits, I will also explain the categorical Langlands conjecture in Fargues-Scholze form. Questions so far?
Using corresponding L parameter, is this just a simple L parameter, or is there this issue that you?
In the second part, I will describe the component C bar. The main reference would be, I will suggest that lecture notes in the IHE summer school. But also, of course, this DHK paper on module space of Langlands parameters. So what is the module space of Langlands parameters? So in our case, this group G is split, so this space is same as the space of form. This is a function from lambda algebra sets and sending a lambda algebra to homomorphisms, continuous homomorphisms from WF to G at above. I will tell you how to compute this space. So, or a certain summand of it. So inside here, there's an open and closed subspace, which is the space of tame parameters. So those L parameter with restriction to the wide inertia is true. WT is the tame weight, which is WF. Talking back here. And there's fact. There is a fact in PDF that this space is same as the space of the so-called discretization of the weight for this WT0, where this WT0 is the subgroup of WT generated by elements with the explicit equation. For Venus X conjugates this topological generator raised to Q's power. So this S0 is the topological generator. Topological of 10 ways. So 10 inertia. So I have moduli sheaves, which is looking to a product of DT prime with T prime multiple. So it's protected, and you can choose a projective topological generation. Okay. So how to compute this space? The example. Example 1. 3 equals to 0, 1. Then, since we have this explicit presentation of this group in the compute space, a closed subscheme of GL1 times GL1, so we just track the image of S0 and covariance here, satisfy a single relation. Y equals X. Okay. In this case, since this group is commutative, so this is just X. And we just have related X equals to X cubed, and there's no restriction on Y, so then we get mu minus 1 times L1 of M. So then we can show that the connected component are of the form mu L to the K times the M, where K is maximal, such that L to the M is divided. Maybe we can put compute the connected component of mu q minus 1 over FL bar. And then we'll see that the picture over 0 bar is like this spectrum 0 bar, which has a closer point, which corresponds to spectrum FL bar, and the open point, which corresponds to QL bar. And then the mu L to the K will be something like this. So on the special fiber, you collapse to 1 point, so it becomes connected. But on the direct fiber, there are L to the K different points. Why circle just? Because in our case, it's the 1 point. No questions?
And also in the same thing is I test this on the one WS, the has capital R, but no, you take some extra. One good circle is value in the FL bar point.
No, like this is my setting. I just start with like the simple objects in the root category. Root category over 0 bar is like 0 bar module with the GF function. And if you consider simple object there, then always they are just live over the specifier. So they're already defined over FL bar. For example, 0 bar as a 0 bar module is not simple. It has irreducible quotient FL bar.
Okay. But QL bar is.
Yeah, right.
They are restricted to torsion.
Yeah, yeah, right. Yes, but this is what I want to start with.
Not simple as zero bar. Between simple, no, like there are irreducible. They're not irreducible if you look at them as zero bar model. Okay. Yeah. No, sorry. Yes, you're right. Yeah, you're right. Okay. Yes.
Then I will extend the example of 0.2. In some sense, this will be analog to the 0.1 case, because this mu LK again occurs. But in the end, this K will be different. So here, this K is such that L to the K divides Q minus 1. But for GL2 case, it will turn out to be the maximum integer that divides Q square minus 1. In the end, it's because like for the finite groups of E type GL2 FQ, there's a non-scale tolerance, which is of order Q square minus 1. Now, example 2. Even fields. In this case, all irreducible 10 L parameters. So these L parameters I want to consider are of the form Different from the way you for degree 2 extension. And the character zeta is d over f is the degree 2 on extension. And the way of degree 2 on extension is just the inertia is the same as f, but the frobenius becomes frobenius square. Like the field is bigger and the Galois group is smaller. Irreducible 10 alpha. So this C alpha need to choose this trigger on the y inertia. C W E maybe model with the same up here. And to compute the kinetic component over the I actually compute the then let this C equal to the induced transition of this feature. So this I view it as a quasicoherent everything real. Okay. Then on the nice basis, if you choose a nice basis, then you can express this L parameter as explicit matrices. So this would be the diagonal form. If I fill out this homological generator, and then use this form, and the frobenius is of anti-diagonal form. Okay. To compute the kinetic component, I fixed the notation. So because we want to compute the kinetic component over 0 bar, this I consider the restriction of the C to the from to L inertia. IFL. IFL. And IL is the maximum of orders of 4 orders of one cell. Okay. And let's draw to be the image of C1. In particular, this C will factor through the normalizer of here, and then I consider put forward to this component group. So as I said, this is just the set of connected components, but there is also a group style. Okay, so this is something discrete. So if you want to use end up with something connected, then you really need to fix the image in this discrete. Okay. Then the theory of modular space of L parameter tells you that the connected component of the space of a cycle containing this L parameter phi is isomorphic to first I come from the formula and the next line. So we have the normalizer of CL. And then you look at the element with restriction to IFL equals to CL, and also the image of the L parameter in here is then as C bar. And then you quotient out by basically the stabilizer. What does this mean? Well, you have the map from right hand side to left hand side, which is okay. Maybe I should first say what this is. of L parameters is prime such that the restriction to IFL is here, and the image in the component group is also set on T. Then you have a map here, which sends GC one to the conjugate of C1. But this map is certainly not a bijection, so you need to divide out the stabilizer of this map. So this isomorphism involves some resulting that P or in the adherence paper. And this roughly says that the connected component containing this parameter L parameter C is same as consists of the L parameters with restriction to IFL and whose image in this component group is in fact conjugacy to the original one. Okay.
So what is the definition of X sub P?
Oh, sorry. The connected component of P1. But also this is same as the connected component containing C, because like this C specialized is fine.
But what's the difference between X3 and C3?
Okay, C3 is the connected component of the set of L parameters. Other question? Then this thing you can compute explicitly because normalizer of the restriction to the parameter L part, it turns out to be just the normalizer of this element S0, and then the centroider of this element is just the diagonal torus, and the normalizer is just the normalizer of this diagonal torus. And if you fix this connected component here, then this is basically a space of cosine over torus. So you can compute similarly as before. So in the end, this will just be isomorphic to, so if I denote set P to be the centroider of the L, basically the centroider of this element, and then this will be the part of the torus where the value acts by raising to Q's power. The ultimate connected component. And this is similar to the computation before that we did mu Q minus 1 times Gn. So in the end, this will be mu L to the K again. But this time K divides L to the K divides the square minus in the end. And then the rest of the formula. So this part T is also normalized of the L. It's the identity component. And I can show us because it's already connected, this B bar doesn't have to. This is same as the central this is okay. And this also right explicitly is just given by me, and you basically want to keep track of the image of the topological generator for Venus again. But these two matrices are all formed. This is diagonal and diagonal. So you need to conjugate back by this L parameter of C. Then you really end up in torus. Okay. Like maybe you can just take this hash moduli. Okay. So then this implies that the categorical component of the stack of L particles. If we model out G hat, basically we kill this G hat here. Because the quotient by T and the quotient by T continuously. This is the last mu L to K and T. And you can see that the Tx by conjugacy on this image of S0, so it acts trivially on this mu L to the K part. But although it looks like this might be a trivial action, but since here you tested by something, the Y elements were tested by something of anti-diagonal form, so this action is in the end not trivial, but you can also write it explicitly. So it's T1, T2, X on AB will give you T1, T3 inverse A, T1 inverse T2. And then you can compute this thing to just A times Dn. What is Dn? Well, here this is really the trivial action. Okay. So then we get the desired result, but the particle sheaves on this thing is just particle sheaves. And this GM. And the point of the GM things will give you some grading because the particle sheaves of the space decomposes according to the character of the GM, which is asymptotic to Z. Questions?
I didn't really follow the computation, but can you just say in words, like what is the mu L, what is the GM? One of them is the Frobenius, the other is, for example.
Yeah, mu L is basically the image of this homological generator. And
Frobenius inertia.
Yeah, right.
Jam comes from the
Well, like, yeah, this copy G comes from the Frobenius.
Okay. Quotient jam, what's the quotient jam?
This is like, I don't know.
So automorphisms.
Yeah, maybe also.
Scalar automorphisms.
Clear from the definition that C5 is the connected component of.
Not clear from the definition. You need to prove something. That's the 5 of that. Now we can explain the transition style.
You write new LQ with the P comma.
Yeah, this you really need to do some computation. So basically, because if you don't take either the component, then this will be mu Q squared minus 1. It will basically comes from the this problem.
I mean the LP, I mean the power P.
Yes. So K is the maximum integer such that L to the K divided Q squared minus 1. So, consequence of both the first part.
So how much of this example changes for a ramified extension?
Well, I think in the end, then the result would be the same. Again, just the GM or the GM, but I haven't done the computation. Maybe complicate. I want to spend the data side. Of representations with zero bar coefficients containing a given zero supercuspidal quantities. Let me just start from G equals 0, 2. If you recall that all irreducible just 0 popular confusion. 2 of the form. The complex induction from the categorical, and there's 10 to the center, and then you induce to the full from row. So we'll show you the expansion of our translated lambda. On lambda 2, the parabolic subgroup. And lambda 2 is the inflation of the representation of the finite code. So the representation of the FQ, where FQ is the relative. And this topic. And to describe this block of the geometric group, in the end, it is related to the block of the finite group. So there's a result by Roy. That's represented T inside T of FQ to be an elliptic torus. So a torus which is not containing any proper parabolic subgroup. In geometric case, this is just anamorphic to FQ0. Then the linguistic induction which induces the difference of category between the block of the torus and the block of the G. So the linguistic induction RTG induces the difference of category. Containing character theta in general position. In order to the block of the group here to contain lambda, where this lambda is the linguistic induction of the character in general positions, which is a irreducible cuspidal representation of the finite group of the type. Okay. And this category is actually very explicit. So this is actually the root category. So this everything is over 0 bar. And so this is the root category. So the order L part of this torus. And in our case, this torus is of order Q² - 1. So this block is really just isomorphic fields. The representation category of zero LKZ. Where LK is again, this K is again maximal such that L to the K divides Q squared minus 4. The same thing for the L parameter side appears here. And from this, by inflation, it is not hard to see that if you consider the representation of the cohort subgroup extend to the center, containing this row here. So I have lambda then inflated to the cohort subgroup, and then I extend to the center of this row. This group is really just the cohort group. I can get it for my row. Product will be then the block of this thing will just be the block of cohort and the product with the block of this integer. Really just and the block of the cohort would be equivalent to the block of the finite quotient by this inflation. So in the end, it's just proximal LKZ. The category of this.
I'm not familiar with the linguistic reduction. Yeah. What's the difference between the linguistic reduction and correspondence reduction?
It's very different. This is constructs via some linguistic variety. Take the cohomology of the linguistic variety.
Yeah, that's it.
But you all need to know that, like, if you input a character in general position, you will end up with a faster representation of this finite group of D type.
But why don't you direct the parabolic induction?
You cannot use parabolic induction to get irreducible cuspidal representation.
Okay.
I have a question regarding the thing you called, so blah blah blah, depth zero is the cuspidal, and then but you say it's inflated in the end from a cuspidal guy. Will it be supercuspidal? Does it not make a difference here, or I'm confused. I thought it should be supercuspidal if you want to induce the supercuspidal.
For 0, 2, this makes no difference.
Right. So the chronology actually exists. Finite groups are D type.
But he is right. You need to induce a supercuspidal if you want to get a supercuspidal.
It would matter for GHU actually.
I think there's this example where Langlands can have another. The actual arbitrary representation can both the sub and the quotient. Yeah, certain small characteristics, and then there's this middle piece. When U is equal to 5, there is an example.
Other cuspidal representation comes from the linguistic induction.
So you see this, and this category is really just like the same as the category of the group algebra. The group algebra in this case is same as the real functions near L3 and here, which is really just near L3. So they would really expect that the compact induction from this parahoric to focus would be a recurrence of category, and this is one of the math areas that in my master thesis. Compact induction. And The category of the block of the earth containing pi. So pi is the compact induction of the. Oh. Then you know this by beta Roman or B Roman. Or this C pi. Now so first you put the replacement. This is the computer home expected GOF by X is the G of the one. This is then computed as usual by Frobenius residual system 94. For example, similar to the computation which now NEX did local Langlands 2. This will be the home of the one row 2 to start with. The hard part is the static vector. What do you mean? Block is the indecomposable sub-abelian category. So this the partition category they will block they will decompose into a product of some sub-abelian categories, and blocks are the indecomposable ones. Indecomposable submets. How to for the essential subjectivity, I'll construct some explicit projective generator of the category on the right hand side, which is also formed from compact induction. So once you have the projective generator, which is in the essential image of compact induction, then you can resolve any other object by this projective generator, and you can show it's essentially subjective. So, compact induction of sigma restricts to the block B of rho containing rho. Is generator, so it's a projective modules, and then it's the generator so determinants of this block containing pi. Well, the sigma and to be the induction from the first filtration group of the following to KZ of this trivial representation where K1 is 1 plus T, 1 plus So the projectivity will be so in the procedure of the generator property. So I will just show it the generator, which means I need to show the home point to any object is non-zero, so that you can resolve any object X inside this block by some copies of this projected generator. And well, the key fact to notice is that okay, let me denote this by pi rho. Sorry. So this is pi rho here. The key fact is that capital pi, which I denote this induction from K1 to GF of the trivial representation. This is the projected generator of a bigger category of depth-zero representations. And this pi rho will be a summand of this capital pi. Capital pi will be pi rho direct sum with complement, which I will denote by pi alpha rho, where the pi alpha rho is the contact investment from KD. Similar to the definition of pi sub rho, but this time you restrict this sigma to the complement of D rho, the complement. So the rest of the block. So in particular, since this pi rho appears as a summand of the projected generator, then it's projected again as a GF module. Okay. Then another important thing is that you can compute by Fargues reciprocity and lective formula again that these two summands, they don't interfere with each other. So the home between them are the of rows and up row then up row. So since this pi rho is a summand of a projective generator of a bigger category, and the complement of this projective generator doesn't interfere with pi sub rho, so we can conclude this pi rho is actually a projective generator of summand pi to start with. We can add a form with category of here, object zero. By important property by the projective generator. So this home from the projective generator would induce its category, equivalence of category to a category of modules. The category modules of the annual module of time. This is the equivalence. And this C pi is the summand here. It was also mapped by this home, but in pi decompose it, so you can write it as pi sub rho this was this And the morphism category will also decompose it because the form between them are zero. But this block by definition is indecomposable, so it can only go non-zerally to only one of these two factors. And you can see that if you plug in pi rho again here, then this goes non-zero here. So it must goes to zero on the bottom. So pi indecomposable as a any category implies that the form from the upper row is zero on sequence. And then this together with the fact that also direct some decomposition and also this zero again. This will imply that this was same as home from pi because upper row x equals to zero. And then this is, but since it's okay, maybe the lead right one more step from pi. Okay. So this is zero. And since this capital pi is a projective generator, then by definition of the generation property is not for any things like the pi. Okay. Okay, so this is this ends the proof of this theorem. So if you have a project generator, which is in the image of the compact induction, then for any other object, actually can resolve it by projective generator, by some copies of this projective generator. And you can show that this X also lies in the essential image. Okay. Okay. Then I think 5 more minutes. Maybe I can also say something about so actually from this explicit description, I think it's not very hard to prove the corresponding part of the categorical local conjecture in Fargues-Scholze form using computation. Zero. So a irreducible representation is called depth-zero if it has a K1 instead. But you can just think of them as these representations that I constructed in the beginning of this section for this compact induction from KZ to G. And the fourth here, there's in Fargues-Scholze form. So in the end, I think this will boil down to the following argument. So if you have some curve into categories which are isomorphic to basically A modules, You have an action of a module on these two sides, which will in the end come from the spectral action. First set first and stands A and F is so under this identification, and F is a moduli action linear. So it respects this a module action. Then this F is an equivalence of category. Equivalence of category. This is not very deep. Don't think so defined. And then in our case, not really an A module, but would be perfect. Perfect complex is on this component. And this category C would be there's some scary decorations, but in the end, people be in favor of that because these are defined such that the categorical local Langlands will hold. So in the end, this will be the same as for D5. And the category D would be the fusion on D. Would be a vacuum. And you consider some about by theta. And the doctor was in the end given by the spectral action. Difficulty. And we can check that actually by the computation before, in the end, this category D was the same as curve of theta using the computation before. Using version I is having like this function. And that is certainly a module linear because it's defined by actions, and there's also stands. You can also check under the identification that it stands the structure sheaf to the structure sheaf. I haven't checked this very carefully, but I think in the end, this thing would be like you can identify all these things to be a structure sheaf. That's F is the equivalence of so I think I'll stop here.
Are there any questions for Chenji?
Important.
Like there's a, I'm also not very familiar with this. In this case, this, there are certain concepts of this near-potent singular support, and in the case of this component, you can prove this is actually zero. I think. I can also explain the computation later if you want. Yeah, like this definition is made such that categorical local ones will hold. So in this case, in particular, this near-potent singular support condition will be not very significant. It will just be zero.
I think this is actually like the main content for mine. Like you're using local Langlands, you're using some kind of compatibility with the usual local Langlands, stuff like that, right?
What? What?
To check even that this D is like not the empty thing.
Okay, sure.
Heavily with local Langlands, and the fact that you already know that this is the correct parameter to assign to.
When you describe the component C5, you showed this only in one example for GL2, and are you saying that all the relevant cases are the computations are exactly the same? So you only showed one example for a tame parameter that comes from red.
All irreducible standard coming from GL2 will be of this form. And you can choose a nice basis such as this matrix is of the form I write.
How far can you generalize your computation to general group?
I think the computations in the section 2 and section 3, so if it accepts the last section, then I think it will, in general, at least for split and the simply connected group. I only assume this split and simply connected for simplicity. In general. So this is the way that sheet. So, I want to for the contact in that. You have to do
Better proof you're going to run into the problem that I said, like you need to know this statically correct.
right.
So you're saying you can prove this or no?
No. In general group, you need to know the compatibility with usual locals, I guess. But you have compatibility, I think, it's not very hard to get categorical.
If you use depth-zero,
like I used this, for example, in the explicit expression. Like otherwise, the construction of the supercuspidal representations are different. For depth-zero case, this should really just come from the category of representation of the finite quotient. It's finite reductive. But for high depths, I guess there's some guess that like there's some work that it can be reduced to the depth-zero case, like both in the representation side and also on the L parameter side. So I'm guessing in the end you can do this high depth case from this depth-zero case, I guess.
all right, let's thank Chenji again.